Okay, let's start. Last time we talked about the pipelining, the core pipelining, the 5-stage pipelining. So we complete the introduction to the CPU core. For the CPU core, the biggest issue is the pipelining. We introduced the details inside each stage of the 5-stage pipelining. And then we also introduced the metrics to evaluate better pipelining, means uniform the sub-operations, dependencies, and some control flow. Today we will talk about cache. So the memory, besides the core, the memory hierarchy is the other very important component in the CPU. Because nowadays we run a lot of big data applications. So you can see that the speed of your CPU significantly increases over years. The x-axis here is the age. The y-axis here is a relative performance. We can see that by the pipelining, by the microarchitecture innovation, the performance of a processor increase a lot. The performance of a CPU, you should remember that Aaron law. We have a CPI. We have the instruction number, but I will not write it here. We have the cycle per instruction. We also have the frequency. We have a microarchitecture or architecture technique like pipelining to improve this CPI. And those microarchitecture innovation also can improve your frequency. And we also have the physical process technology to improve your frequency. So a lot of different factors can help you to improve these two numbers. But for the main memory, you can see that not only main memory, but also the on-chip cache, you can see that the performance only slightly improved. So clearly we have a gap here. So if your application has a lot of memory access, the performance of those types of application will not be good. So this figure indicates the hierarchy of the memory. We have the fattest but smallest registers. We also have the largest, capacity largest, and the slowest disk. Under the register, we have cache. And then we have the main memory, your DRAM, and the SSD. Nowadays, in your iPad or your mobile phone, you may not have a disk, but for some, high-performance server, they still have these large disks. These two types of memory are so-called on-chip memory. They fabricated in the same die or in the same chip as your CPU, as your pipeline, 5-stage pipeline. But you can buy the DRAM as an individual chip. So this is so-called off-chip memory. And the top two are the on-chip memory. These two are so-called storage. The top three types of memory are managed by the hardware itself. These two types of storage are managed by the software. And this is the fattest and also the most expensive one. This is the when I talk about the price, I mean the dollar per byte. So the dollar per byte of registered file is very expensive. On the contrary, the disk dollar per byte is relatively cheaper, but it is slower. Because your application has a lot of temporal and spatial locality, most access can happen in the register and on-chip cache. In this way, we can share. In this way, we can enjoy the good performance, but only have a very small capacity of the register file and on-chip cache. But this so-called temporal or spatial locality do not exist anymore because of the big data application. When you do sorting, when you do lookup table, the hash table lookup, these application has very large footprint. They can easily access your disk, your SSD. So in this way, the spatial locality is not good. So this is the trend for the price. This is the trend for the speed, the bandwidth. So today we will focus on the cache because cache is on-chip. Register files, we talked about these register files before in the pipelining. We have a lot of pipeline registers in the 5-stage pipeline. Today we will talk about cache. And in the future, we will talk about the DRAM, the dynamic memory. So this is the example of cache. Cache is just an enter you call, which can buffer some data for the call. So it's managed by the hardware, which means that you cannot, as a programmer or as a user, you have no influence to the cache. You cannot manage the cache or change the cache configuration because it's controlled by the hardware. The cache should be transparent to the user or the programmer. So we can break the cache into blocks, several bytes. Typically, each cache line is one block is called one cache line. Each cache line is 64 bytes nowadays. And when we fetch a piece of data, transfer a piece of data from the cache or to the cache, we do that at the granularity of blocks or the cache line, which is 64 bytes. So we always keep the recently accessed block. So this is the spatial locality, temporal locality. So we have the cache line concept, the minimum unit that you can cache. We also have the frame. Frame means the physical location of that one cache line. The frame is the concept of the SRAM cell. So the cache is implemented by the SRAM, static memory, RAM. 64 B SRAM cell is called a frame. the data, the logic concept of data is cache line, is the block. When we actually can find a piece of data, at this time it's called a heat. If we cannot find, then it's a miss. The miss ratio means the fraction of references that missed. Heat time means the time to access the cache. Miss penalty means the time to replace a block on a miss. So I will introduce this concept in the following slides. So the miss ratio means, for example, you have 100 access to the cache. Maybe only, let's say, 20 accesses can be found in the cache, which you have 20 hit, but you have 80 misses, okay? The fraction means you use 80 divided by the total access number, which is 100. You use 80 divided by 100, then the miss rate is 80%. So this is so-called miss rate. And the hit rate is 1 minus miss rate, which is 20%. So let me give you one example to explain the cache. Assume that we have these memory accesses, and assume we have 8-byte cache line. So previously I introduced we have 64 bytes cache line, but in this particular example, the cache line size is only 8 byte. This is cache. Okay, this is main memory, this is cache. At the beginning, we try to access the cache, but the cache itself is empty. It has no data. So the first one is always missed. This miss is called code miss. So we need to fetch this piece of data from the main memory back to the cache. Because each cache line is 8-byte, even we access this 140 address, we actually fetch the data from this address to 10008 address. So this line indicates the address from here to here. So next time when I try to access this address is actually between these two addresses. So we have, which means that this piece of data includes this address. So we have a heat here. When I try to access this one, apparently we do not have this address. And we fetch another line here. Again, this line is between 10120 to 10128, because each cache line is 8-byte. I'm sorry. Each cache line is 8 bytes is from 0 to 7. From 0 to 7. So for the fourth accesses, for the fourth access, even we access this 1.8, we cannot find it. It's a miss. We fetch it from a main memory to cache. So this piece of data should include from 130 8 to 1 2 zeros 1 5. For this address, we find the heat because this one can heat between these two addresses. For the last one, we have a heat because it's the same as the second access. So you can see that the absolute value of the accesses we have for some accesses, the absolute value of the difference between the addresses is small. This is the reason why we have a spatial locality. These are the spatial locality. And sometimes we access we access the same address. These two are the same address. This is so-called a spatial locality. I'm sorry, the temporal locality. In a short time, we access the same address. This is a temporal locality. And the absolute value of the address difference is small. This is the spatial locality. The spatial locality means if we access this one, which means that the next time in the future, it's very likely for us to access its neighbors, which is exactly this one. The temporal locality means if I access this address, in a very short time, later I will access the same address too. So this is the temporal locality. So in this way, the miss ratio is 50% because we have 6 access. 3 of them are hit and 3 of them are misses. In this slide, we can calculate the average memory access time. Average memory access time.
Professor, I had a question.
Yes.
Suppose like the L1 cache, it misses. So does it go to the L2 cache or can we directly go to the RAM?
In the previous example, we only have one level cache, but we will talk about multiple level cache case in the following slides.
Okay, thank you.
So assume that cache hit is a 10 cycle, memory access is a 100 cycle. If the miss ratio is a 50%, then the average access latency can be calculated as this. So if the miss ratio is 50%, then half access will get a hit, but the other half will get a memory access. So we use a 50% multiply 10 and 50% multiply 100 and add them together. This is how we calculate the average memory access latency or average memory access time. If the miss ratio is 10%, 90% get a hit. Only 10% get a 100. So if the miss ratio is 1%, 99% get a hit. Only 1% get a 100. Then the average memory access can be calculated as the last line. So you can see that by improving the hit rate or decrease the miss ratio, we can significantly reduce the memory access latency. So you can consider if we have a multiple level of cache, we have L1 cache, L2 cache. This is their access latency and memory access latency. If the L1 cache has 20%, L2 cache has 40% miss ratios. How to calculate the average memory access time? So if the miss ratio for L1 cache is 20%, then the hit rate is 80%. So 80% access can get a 5-cycle hit. And then the other 20% will get the rest. So how to calculate the rest? All these 20% accesses, among all these 20% accesses, 40% of them will get a miss, will go to the main memory, will have this 100%. The other 60% will get a 20 cycle, which is a hit in the L2. So this is the 20% case from the L1 perspective. And then we sum them together. The result is a 14. So here you can see if you cannot further improve the cache hit rate, you can add more level of cache. In this way, you can still improve the average memory access latency. So in a general case, we have L1 cache and L2 cache, L3 cache, even the L3 cache. And the L1 cache is a split. We have a L1 instruction cache, L1 data cache. So the instruction and the data are separated. And we also have a L1 instruction. This is a so-called translation lookup buffer, TLB. The TLB is used to translate the virtual address to physical address. I will introduce the physical address and the virtual address in the following lectures. But these two are also separate. But these four will be combined in the L2. So which means that the L2 cache can contains instructions and the data. And even the translation between the virtual address and the physical address. So all these can be put into L2 cache and can be put into L3 cache. Nowadays, you have multi-cores, so core 0 and core 1. These two cores can share a L3 cache, but they have their private L2 cache. The so-called share and the private is some kind of trade-off. For example, if you run a memory non-intensive workload on core 0, the application use only a little cache, but you run a very memory-intensive workloads on the core 1. So the L2 cache and L1 cache on core 1 are not large enough for the applications. So in this way, if these two parts are private, then even these parts are idle. The application running on core 1 cannot use them.
I had a question.
Yes.
So if we overclock a processor, does the cache also get overclocked? Like we can overclock the RAM, but does the cache also get overclocked when a processor is overclocked?
Like the previous figure shows, it's really difficult to decrease the latency of the memory. When you do the overclocking, you cannot overclock the cache.
Okay.
which means that your overclocking only works for the application which do not use the cache a lot. If your application is memory bounded, then overclock doesn't help.
Right, right. Okay. Thank you.
But again, for the memory intensive workloads, they can use the L3 cache because the L3 cache is shared. So this is a physical layout for the core. You can see the shared L3 cache is very large. We will introduce the SRAM cell in the following slides, but I can tell you that the SRAM cell is very regular. It's very structured. So you can see these regular structure are the memory. Even for the core, this is one core. On the core, the regular structure are memories. So you can see that the memory may occupy, I can say at least 50% of the chip area. So the memory means a lot for a CPU. So this is the SRAM of SRAM cell. SRAM cell is very simple. It's just the two inverters. This is the first inverter, the second inverter. When we store one here, the input of this inverter is 1, then the output is 0. The input of this inverter is 0, then output is 1 here. So it's a stable state. This is so-called SRAM. So the state is stable. Two inverters connect together. Again, if we store a 0 here, the input of this inverter is 0, then the output is 1. For this inverter, the input is 1, the output is 0. It's also stable too. We use another two inverters to read the data out. And these transistor can control whether we need to connect these two inverters to the cells here. So each inverter you can look up our slides about the VLSI design. This is a pull-down network and a pull-up network. This is one inverter. The one inverter has two transistors. So we have a two transistor here, two transistor here, and another two transistor here. These are so-called, these two are the sense amplifier. It's not the cell. These two are the sense amplifier, so we do not count them. So this is a so-called 6T, 6 transistor SRAM. So this is so-called 6T transistor SRAM, 6T SRAM, I'm sorry. So 1 bit costs you 6T, 6 transistor, which means that the SRAM is actually very expensive. But still, we can have multiple cells here. So you can compare this figure against this figure. So you can see that we have this row, this line. This line is so-called one row. This line is connected to the transistor. So assume that we have one line here, and that's the row line, and we connect these two to the line. Okay, which means that if I put a 1 here, these two gates will be closed. Closed means connected. Connect means these two sense amplifier can read the data, can access the data here. So if all the cells here share the same line, then by providing a one here, I can access all the cells here. And the data of these cells will flow from the cell to the bit line. The vertical line is the bit line. So when I apply a one here, I can get the data here, right, for each cells. So by this one single signal, I can control all the cells in one row. This is the row is so-called word line. Typically, we write one word. Why we want to write one word? Because everything is a byte addressable. One word on some machine is 1 byte, or maybe 2 bytes. And this vertical line is the bit line, which actually give you the data, the content. So the horizontal line is the word line, vertical line is the bit line. And we can have a multiple word line. These word line can share the same bit line, okay? But each time you can only enable one word line, like this word line. And only this word line can put their data on the bit line, and we can sense the data through the bit line. Can we simultaneously active two word lines? No, we cannot. Because if these two cells put their data on the same bit line simultaneously, the data will be messed up. We cannot do that. So we have to access each row sequentially. With the SRAM structure, we can have the cache. So this is the cache structure. Apparently, the cache is help you to buffer some data. So this array is help you to store the data. When you have the data, you need to do the lookup, because sometimes I want to look up this address. I need to make sure whether the data has this address. So we can store the address to the tag, so that when I have an address, for example, all zeros, I can compare my address to the tag. If I find the tag are the same as, one tag is the same as my address, then I have a hit here, okay? So the most two important part is the data and the tag. And we also have some state registers here. State register indicate whether this piece of data is valid or not. Particularly, they are useful when you have multiple cores. You need to maintain the cache coherence. But in this lecture, we will not introduce these states a lot. We will focus on the tag and the data. Because nowadays you have a 64-bit machine, so the address can be from 0 to 63. Okay, these are the 64 bits. In this example, the block offset, the data offset is only 6 bits. By 6 bits, we can address 226, which is 64 bytes. So each line here is 64 bytes. And all the other parts are the tag. You can see that for the address, only the least significant 6 bits is used for the data, and all the other address for the tag. For a fully associated cache, I can put the data to all the entries here. any entry can store any address. So when I have one address, want to do some lookup to see whether this address is actually contained by this cache, I need to compare this address to all the tags simultaneously. And then I will see this is a AND gate, and then I will see whether I have a hit or not. So you can see the comparison operation is very expensive because this comparison operation needed to compare a lot of attacks. If the cache size is very large, the comparison operation will be very slow. So the benefit of the fully associated cache means one line can hold any data. Any address can be stored in this line. So the hit ratio may be high in this case. This is a benefit, but a disadvantage is during one lookup, you need to compare your address to all the tags here. The comparison operation is very slow. So when the cache is full, when there's no free empty space, we need to do the lookup. And the state here also can help you to record which line is the least significant, least recently used, and which line is the most significantly used. And these states can help you to do the replacement. Typically, we use the LRU, least recently used. We kick out the least recently used line out and fetch a new line here. That's the cache replacement. So we have three different types of cache misses. The first one is a compulsory. Compulsory means we meet a line we have never met before. For example, the code cache, code start. The second one is a capacity. The cache capacity is small. We have to frequently, do the replacement. The third one is a conflict. The conflict means it's not a compulsory or capacity issue. It's some other issues, but the fully associated cache has this issue, has no conflict. Why? Because one physical line here can hold any address. So there's no conflict in the fully associated, but we will introduce this problem in the following slide. We have still another cache miss, which is a coherence. But in this lecture, we will not cover the multi-core issue, so we will not go deeper on this topic. The cache size is very important. The y-axis here is a hit rate. The x-axis here is a capacity. We can see that if we have a very small cache size, the hit rate will not be high because we have a lot of complexity, misses. When we improve this capacity, enlarge this capacity, we can reduce this type of misses, and then the hit rate will go high. But at some point, it will be saturated. We will still have this compulsory and conflict misses. We cannot solve these two types of misses by only increasing the cache capacity. Further increase the cache capacity will not help the hit rate. But a larger cache means long access latency. Why? Because if you have more tags here, the comparison operation will cost you longer time. You need to compare against more tags here. So the latency of each access will be prolonged. Although the hit rate is reduced, but the latency is prolonged. This is another problem, another trade-off. So a larger cache doesn't represent a better performance. You do not like a too small cache or too large cache. You prefer a, medium-sized cache, which is the sweet point of the trade-off. And the block size is another problem. Larger block size can help us to improve the spatial locality. You should remember we have this example. When our first access fetch this address, we actually also fetched this address. So this address actually is also put into the cache. When we look up this address, we get a hit. This is so-called spatial locality. So when we increase the block size, which is a 8-byte in this example, when we increase this number, we can increase the likelihood to get this line. This is good. We improve the spatial locality, but we cannot have a very large block size. Otherwise, we will introduce a lot of wasted data. The data we will never use in the cache. So we also have a sweet point here. Back to that example. If we change this one to maybe 1K byte, we fetch one line and then the cache is full because the cache capacity may be only 1K bytes. And then for the following address, we always fetch 1K byte, we stretching the cache. In this way, we do not want to have a very large line size or block size. Again, for the block size, we also have a sweet point here. We can add a decoder here to access one line. This decoder can help us to activate this row, and then we can fetch the data of this row through the bit line. In some cases, we do not want to read the data in all these cells. We can also add a mask here. This a mask is also a decoder. So we can only select maybe one bit here by this mask, only read this one bit out. So in this way, we can control this array at a fine-grained style. We don't have to read all the data in one row. We can select several bits. And we introduced the fully associated cache. Now we will introduce another type of cache, which is a direct mapped cache. Again, for the fully associated cache, one frame, one physical line can store any memory data with any memory addresses. But the lookup is very slow. During one lookup, we need to compare the address of my request to all the tags. And that will be very, very slow. And it's not a scalable, so-called scalable anymore, because it cannot support a very large cache. This is the reason why sometimes maybe we prefer a direct mapped cache. Direct mapped cache is simple. The idea of direct mapped cache is simple. Assume we have 1, 2, 3, 4, 5, 6 address, and the cache only have 0, 1, only have 2 entry. So we can use a mod operation to decide which address go to which cache physical location. So when I have this address, we can do a mod operation, mod by 2. So 0 go to 0, 1 go to 1, 2 go to 0, 3, I'm sorry, this is 3. 3 go to 1, 4 go to 0, 5 go to 1. So by a mod operation, I can know the cache address by my request address, cache location by my memory address. But in this is so-called direct mapped cache. But by this direct mapped cache, some address can, one cache line location can only store some address. For example, this 0. This 0 can only contain the address whose mod is a 0, right? So in this way, we have the index concept. The index concept is the mode results. And we still have this block offset, which is a 6 bits, which is a 64 bytes. We have index bits. The index bits is from 6 to 15, which is 10 bits. By 10 bits, we can index 2 to 10, 1K entry. So if we have a 1K entry, then the address need to mod 1K, mod 1K. And we still have the tag. Why do we have a tag? Because 0 and 2, these two lines can store in the same location. In order to distinguish whether it's a 0 or 2, we still have this tag to do the comparison. When we have an address, for example, my address is 8, I don't need to compare all the tag against my address, which is 8. So in this direct map cache, I can directly get a mode. My mode address, my mode result is a 0, of course. And then I can directly go to this 0 entry. But even when I go to this 0 entry, I do not know whether this entry have my data or not. I need to compare against this tag. Maybe this 0 entry store this 0 address. So in this case, I still have a miss. Maybe this entry get an 8 address, then the tag are exactly the same. I can get a hit. But during this access, I only compare against the one tag. So in this way, I can significantly improve my access latency. But each cache location here can only store some of the address. In this particular example is the mode relation. So the cache hit rate may be low, but each access latency is short. For the fully associated cache, each line can store any address. The cache hit rate is high because we can fully utilize the cache. But during each lookup, we need to compare a lot of tags here. The cache access latency is long. For the direct mapped cache, we have some restriction on the memory address one cache location can store. So the cache hit rate is low. But during each memory cache access, I only need to compare against the one tag. So the access latency is short. So these are the trade-off. You need to remember the difference between these two types of cache. So why we need to take these bits out of the middle? Why we do not use these bits as the index or these bits as the index? Why we select some bits from the middle? This is because by doing this, we can take advantage of the spatial locality and the temporal locality simultaneously. Think about this. I will explain this point in the next lecture. But here I will introduce a little bit about the index, the address index. So here is some address example we will access. If we use the middle bits as the index, they are the same. Basically, for these three addresses, they are the same. And the offset address, they are the same. But of course, the tag are different. If the index are the same for these three addresses will be mapped to the same location here, because the index of these three addresses are the same. So they will have so-called conflicts. This is the third type of cache misses, which is a conflicts. And of course, the tag are different. So by comparing the tag, we can exactly know the cache line store which piece of data here. So you can see each character here indicate 4 bits. And the 5 character here are the same, which is the 20 bits. Are the same. This is a very common case. Why? Because if you have some structure has 20 bits the same, you try to, you try to access your array elements. Each element is 20 bits. Then this is the case will happen. In this case, we will have a lot of conflicts. Although we have enough memory capacity here, these 3 addresses will be mapped into the same location. So they will have conflict. Even all the other memory addresses are empty. Even all the other cache locations are empty. We cannot store the data in those locations in a direct mapped cache. We have enough capacity, but because of the conflict, we cannot simultaneously hold these 3 pieces of data in the cache. So in some sense, we hope that we can combine the direct mapped cache and fully associated cache. Then we create a concept named associativity. So for the fully associated cache, one memory address, one block, one cache line can go to any frames, any cache locations. So we call this concept, we call this phenomenon as all frames are in one set. But for the direct mapped cache, each block can only go to exactly one frame. Each cache line can only go to exactly one frame, one cache location. So this is a so-called one frame per set. One line here, one cache location here is one set. We can extend this set concept. We can use 2 frames in one set, and we can have multiple sets. So this is so-called set associativity concept. We have the set concept here. We have 4 sets. And inside one set, we have 2 frames. So if you have this block, this memory address, this address can go to any location in this type of cache. And this address can go to exactly one location. One location. And this address can go to one set here. But inside that set, you can go to both frames here. So by the set associativity, we can combine the block and the set concept. If you have so there is a trade-off on the set associativity too. A larger associativity, which means your cache is more like a fully associated cache. Then the miss rate is low because it's more like fully associated cache. Each lookup, each memory access will do a lot of comparison. If the associativity is smaller, then it's more like direct mapped cache. The cost is low because each memory access only do one tag comparison. The hit rate may be low, but you will have a faster access latency, a smaller access latency. Then again, select a medium size of associativity is also very important. Then we have the n-way set associativity. We have index, block offset, and text. We also have 2 ways here. So this is the first way, and this is the second way. And we have sets here. When we choose one set, the data can go to any way of the cache. So simultaneously, if we want to do the lookup, we need to simultaneously look up these 2 entries. Because the one data can be stored in both ways. I think the most important concept is the set associativity here. Let me summarize it again. For the fully associated cache, you can store any block or any cache line to a frame or to a cache location, physical location. This is good. This can help you to enlarge your cache hit rate. But when you do the lookup, when you do the cache access, it brings you troubles. You need to compare against a lot of tags because one line is possible for one line to store all these positions. You don't know which position it is stored. It is stored. you have to compare against all the tags here. So the hit rate is high, the memory access is slow, cache access is slow. Then people propose another type of cache, which is direct mapped cache. They introduce the concept of the index. The index is the mode results of your address. For example, all address need to mode by mode 2 to calculate this index, and you can only store your data to this particular index, which means that you only have one option. So each memory, each cache location, physical location can store the memory address whose mode is 0. So in this way, the cache hit rate is smaller because you have less choices. Even some other memory cache location are empty, you cannot store the data in them because of the index problem. And if you have a multiple line simultaneously want to store the data in this index, you will have a conflict. More conflict means smaller cache hit rate. But during each cache access, the latency is shorter. You only need to look up one tag, compare one tag. So this is the trade-off. In order to balance these two trade-offs, people propose a set associativity cache. So they combine the set and the way into the same cache. To simulate the direct mapped cache, we have the set concept. So one particular address, for example, in this case, mode 4, one memory address mode by 4. So one memory address can only choose one set. You can only choose one set. But inside one set, you have two options. So inside one set, it's more like a set fully associated cache. You can store you can choose any of these positions. But at the set level, it's like the direct mapped cache. You do the mode operation, you can only choose one set. But inside the set, inside one set, you can treat it as a fully associated cache. So in this way, you compare against less tag, but you can also maintain a reasonable cache hit rate. And then the set associativity means it's not, too large is bad because too large is more like a fully associated cache. Too small is also bad. It's more like a direct mapped cache. So we need to choose a reasonable number, medium number here. Any question on this? If no question, please review this. I know it's difficult to understand. That's the reason why I explained maybe 3 times in this lecture about this, about the fully associated cache, direct mapped cache, and the set associativity cache. Try to understand it. That if you have any question, please email me. Otherwise, we can stop today. Thank you very much.
Thank you.